Let me tell you about one of the youngest and most exciting areas of astronomy research. This is a field that is so riddled with diversity and discovery that astronomers are constantly left going, huh? 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 Yes, it's finally happening, everyone. We're doing an episode on exoplanets. Exoplanets are planets outside the solar system, so typically planets orbiting any star other than the sun, but some of them are orphaned and have no star at all, so just outsiders, really. And honestly, the stuff we've been discovering is just constantly challenging everything we think we know about how planets form and evolve. I tell you, it is wild out there. In fact, it is so compelling that back in 2018, I left my lovely, stable job as a secondary school physics teacher, moved to the Midlands, and embarked on a PhD in astrophysics as a mature student. I had to learn Gen Z slang to get the cool kids to talk to me. And lucky for you, tonight, you're gonna get a taste of the field I love so much without having to leave your job, or even your sofa for that matter. Welcome to the Sky at Night.
Humanity has been dreaming of finding planets out amongst the stars since we first started staring into space, asking questions and wondering what might be up there, waiting to be discovered. How lucky we are to be the generation that gets to answer those questions. The first exoplanet around a normal star was found in 1995 by astronomers watching how a star wobbled this way and that, back and forth, pulled by the gravity of a Saturn-mass planet. Such giant planets all lie far from the sun, but this one whizzed round its star in just 4.5 days. No one had expected such a world. And this one discovery spurred on a new generation of planet hunters who wanted to conduct a census of planets in our galaxy. To do so, they used a different technique, the transit method. Thousands of stars are monitored at once, looking for the faint dip in brightness that happens when a planet gets in front of its parent star. Results from space telescopes like Kepler, more recently TESS, have told us that not only is the galaxy full of planets, but that some of them might well be like our own Earth. Now, exactly how Earth-like a Earth-like planet has to be in order to count as properly Earth-like is open to debate. If we assume that life like us needs a planet like ours, cozy atmosphere, liquid water, the right temperature, then results that we have on hand are close to confirming that not only is the Milky Way full of worlds, but lots of them are possible homes. Are any of these worlds actually inhabited? Well, astronomers hope to detect what's called a biosignature, a chemical which might indicate the presence of life. A recent paper claimed to have detected a chemical DMS in the atmosphere of a Neptune-sized world called K2-18b. Now on Earth, DMS is made exclusively by life, mostly by microorganisms, so this is exciting. But the picture is murky. Some people think that K2-18b has a liquid water ocean, others that it's a lava world, and those details matter. Other groups have looked at the same data and found no trace at all of DMS. And even if it is there, can we be sure that it can't be produced without life in the chemistry of such a strange world? People are doing lab experiments to be sure. Basically, this stuff is hard. But in the meantime, don't despair. Don't worry that we haven't yet found our perfect twin Earth, but revel instead in the diversity of worlds that we do know about. There are hot Jupiters and hot Neptunes, warm Jupiters and warm Neptunes, lava worlds, Earth-like places, Venus-like planets, comet-like planets, stripped core planets, diamond worlds, planets around young stars, planets around old stars, planets around pulsars that make no sense at all. There are planets in...
While Chris continues his list of amazing planets that have already been found, I'm in Germany, where a new mission that hopes to find many more is being built.
Dubbed the Planet Hunter, ESA's Plato spacecraft is set to fly about 1 million miles to the L2 Lagrange point, where it's going to unfurl its 9-meter wingspan and settle in for about 4 years to observe about 200,000 stars and the exoplanets that orbit them.
I'm meeting Industrial Prime Project Manager Pablo Jorba-Goloma by a model of the spacecraft. At the heart of the Plato mission is the extraordinary array of precision-engineered high-spec cameras. 2 fast cameras at the top are integral for guiding, while the rest focus on monitoring the stars to hunt for exoplanets.
So talk me through these cameras. They're kind of slightly offset from each other. What does that mean?
Plato has 24 nominal cameras devoted for observation that are divided in 4 different groups of 6 cameras. So we have a first group here of 6 cameras, second, third, and fourth. So all the cameras or groups are tilted in a way that you have an overlap of the 24 cameras in the center. So in the center field of view of the spacecraft, you will have all the 24 cameras looking to the same star to try to detect any kind of dim on the liner.
By grouping the cameras like this, Plato can obtain a wide field of view covering 5% of the sky, while also getting incredible detail in smaller sections where more cameras overlap. But this requires precision, and the extremes of space cause huge engineering challenges.
The thermal control of a spacecraft like Plato is really complicated. We need to understand that the sun-shielded solar array, which is pointing all the time to the sun, will rise to up to 160 degrees Celsius. Meanwhile, the cameras will be around minus 80 degrees Celsius.
That's kind of specific. Why that temperature?
So in average, we are talking about minus 80 degrees Celsius, but each camera has been characterized individually to determine which is the optimum point of operation in terms of focus and in terms of performance of the detectors. For this reason, so maybe one camera is at minus 79.5, another one is minus 79.7. So we have a dedicated thermal control camera by camera, and we are controlling during the whole mission that the camera temperature is always at the same point. Not only because of performance, but also because the temperature of the camera affects also the alignment.
I honestly, I'm absolutely blown away. So every single camera has its own little heater, keeping it stable in temperature to like 1,000th of a degree.
Yes.
Incredible. What stage is the build at right now? Where have you got to?
Just last week, we completed the integration or mating of the payload, which is the 26 cameras and the electronics, with the service model. It was a really, really precise and challenging activity that involved the participation of more than 20 people during 1 week.
Congratulations. I mean, what a massive milestone to have hit. Now, obviously, for an exoplaneteer like me, this is so exciting in terms of the data we're going to get. But for an engineer like yourself, what's it been like?
So on one side, of course, it's technical. We are engineers, we love challenge. But not only this, if we consider the number of institutions, universities that has been contributed for the development of the payload, it's really, for me, something that makes me proud to be in a project it's European.
Okay, so now, can I see the real thing?
Yes, we will see it, but please don't touch it, yeah? Don't touch it.
Plato will be the culmination of the work of over 100 organizations from across Europe, and I don't want to be the one to mess that up. So first, it's time to don some PPE. With that done, the moment has arrived.
So,
It's so beautiful. I was playing so. My heart was racing when I was waiting in the clean room to come out, and like, yeah, he's a beauty. And I was told actually that of the scientists who are going to use Plato data, I'm the first one to see it like mated, to see it like put together. Of the exoplaneteers, I feel very privileged to be here.
This is mind-blowing. I am absolutely obsessed.
All these panels are currently open because we are in the middle of routing all the cables. And what you see here, for example, is the onboard computer. You see also the communication channels or communication panels.
Yeah.
The antenna that is behind.
Yeah. We're going into space. My face hurts.
I'm barely holding it together from down here, but then I was allowed the ultimate view.
I can see all the cameras. Are they in their positions? Like, have they been aligned?
Yes, all of them are placed, integrated, tested, and aligned.
George, talk to me. Huh? Talk to me. I can't. I'm in love. I could stay here all day.
It's incredible to think that in about a year and a half, Plato will be out there scanning the skies for new exoplanets. But in the meantime, we already have a huge sample of exoplanets to keep us busy.
We've got icy worlds and water worlds and ocean worlds and Hycean worlds, super Earths and sub Earths, super puffs, super.
As we discover these bizarre worlds, we have been cataloguing them and plotting them onto graphs. And a puzzling mystery has emerged. So far, we've found thousands of exoplanets, and for the majority of them, we can work out their radii. Now, it turns out that most of them sit between Earth size and Neptune size. Now, Neptune is 3.5 times the size of Earth, but there's a mystery. To explain further, I've got a little demonstration, and it involves sweets. Now, each of these jars represents a distribution of exoplanet size. This one is 1 to 1.5 times the size of Earth. This one is 1.5 to 2 times the size of Earth, and this one is 2 to 3.5 times the size of Earth. Now, these sweets represent the exoplanets, and we can fill up the jars according to their sizes. Now, as you can see, I think a pattern is emerging. But let's put the other exoplanets in, and then I'll explain. So now we've distributed all the exoplanets, you can see where the mystery lies. We have plenty in this jar, we have plenty in this jar, but in the 1.5 to 2 times the size of Earth, there seems to be a deficit. And the mystery is so grand, it's been given its own title. It's called the Exoplanet Radius Valley. Because if you plot this on a graph, you get a valley here in the middle. To find out more about this gap, I'm being joined by Larissa Palethorpe, who's been studying this area, and along the way found more than she expected.
Now, we're speaking exoplanets. Now, we've been doing a demonstration looking at the Radii Valley, and this is the area of your PhD research. Can you tell us more?
So my PhD thesis is called Characterizing Small Exoplanets. Essentially, I look at these planets, which are around Earth size, to work out kind of why we have this gap in the makeup of these planets. Adding new sweets into these jars so that we can learn more about the problem and try and get some answers.
Okay. And I suppose that's it. The sort of more sweets we have, the better we understand the distribution. And you have the proud position of detecting an exoplanet yourself. Tell us more about your exoplanet.
Yes, so Gliese 12b. I co-led the discovery of that planet last year. It's an Earth-sized, very temperate planet, so it's about 42 degrees Celsius on the surface, which makes it a very exciting candidate for follow-up to see whether...
Yes. So almost Earth-like. I mean, 42 is a bit warm, but...
Yeah, so we would classify that as kind of Earth-like, kind of looking at can liquid water exist on the surface?
Yes.
And obviously at 42 degrees Celsius, it could. But it's hard to say whether the planet is Earth-like right now from the information we have. Right now, we currently only know the radius of the planet, so the size of it. In future, we're going to learn more about the mass. That's currently being worked on right now.
Yeah.
But what we really want to understand is, does it have an atmosphere?
So I have to bring it up, life. We don't know about if it has an atmosphere or anything like that, but it just feels quite exciting that, potentially there could be life, maybe.
Yeah, potentially. It's kind of hard to make a claim like that with kind of the way we analyse data right now.
Yes.
But it's definitely a good candidate for looking at kind of a temperate Earth-sized planet and what ends up evolving on the surface of that. So hopefully, maybe it's habitable, but we don't know right now.
Yes.
Hopefully we will know in the future.
And I suppose the other exciting thing is it's not that far away.
So it's actually our nearest Earth-sized, temperate, transiting planet found to date. So,
I love the description.
yeah, it's a bit of a mouthful. So it's near, it's 40 light years, it's Earth-size, it's about 1 Earth radii. It's temperate, it's 42 degrees Celsius on its surface, and it's transiting, so it passes in front of the star, which makes it helpful for observations.
Orbiting a red dwarf star that is just 27% the size of our Sun, Gliese 12b is a fascinating planet. But we still have the Radius Valley mystery to solve. Are there theories out there that might explain why we have this lull?
Yes, there are theories. So it's to do with how planets form and evolve. There are a few different mechanisms as to how we think this might work, but the key base theory is that planets start off with atmospheres, and through some process, whether it's to do with the star or the way they formed, is that they have their atmospheres stripped from them, and hence they become super-Earths. So there are different mechanisms. We haven't been able to nail down the mechanism yet, but essentially it's atmospheric loss.
Okay, yes.
That's what we think.
And this is sort of the transition zone.
Yeah.
And so they start off here, they end up here, and then they just pass through this, and
Yeah.
so there might not be many out there.
Yeah, so theoretically, we should see planets moving through the valley, and depending on the exact theory you choose, is how long it would take them to move through the valley. So that's how we're going to narrow things down. So again, it's adding more sweets to this jar and seeing how long they stay in that jar for before they jump over. Hopefully will help us nail it down.
Well, you can't argue with more sweets.
Yeah, exactly.
We've got planets with clear atmospheres, planets where it rains glass, planets where it rains iron, hazy planets, cloudy planets, planets with rings.
But the planet we really want to find is one exactly like ours. And maybe Plato will be the one to find it. George has torn herself away from the spaceship and is sitting down with Thomas Waleszek, the ESA project manager of the mission, to find out what makes it so special.
So talk to me about Plato's aims. What's Plato going to achieve for us?
So we are really looking for Earth-like planets around Sun-like stars in what people call the habitable zone. So meaning there might be a possibility of liquid water.
What's special about this mission?
I would say we are a multi-telescope mission, which is quite different to the missions beforehand. Beforehand, we had, let's say, single telescopes. We have 26 cameras on board. But also there, we have a blue filter and a red filter on the fast cameras, which could give us a hint about already the atmospheres of these planets.
Now, of course, these are going to be very impressive cameras, but can you put it in terms I'll understand? How many megapixels? How does it compare to my phone camera, for example?
You know roughly the size of your phone, and then we can talk maybe about the size of one sensor of one of the cameras, which has 20 megapixels. But we have 4 of them per camera, which makes it 80 megapixels already per camera. And if you put it to 26 cameras, you have 2.1 gigapixels. So 2.1 billion pixels really that we have at hand to do our observations.
So a slight improvement on my 12 megapixels.
I would say so.
So how important is the stability of the configuration?
Yeah, that's really one of the main drivers of the mission. So we are looking at the Southern Hemisphere as one of our observation fields, and we want to look at this for 2 years. Within these 2 years, what we are trying to achieve is that we have a variation of a target not more than plus minus 1 pixel over the cameras of the camera sensors.
The aim is to have the same star roughly on the same pixel for the full
2 years?
Yeah, that's in principle the idea.
That's astonishing.
Yeah.
Do you think Plato will do it? Will it find Earth 2.0?
I definitely hope so, and let's say statistics show that we have a chance.
It is thrilling to think that one day Plato may detect other planets exactly like our own. But while we wait to find out, an unexpected gas giant is challenging our understanding of how planets form.
TOI 6894 is a faint red dwarf, nothing to write home about, and normally a star no one would pay attention to. But a paper out last month revealed that this star has a planet all of its own, and it's one that shouldn't exist. I'm at the University of Warwick, meeting Edward Bryant, who discovered this planet to find out more. So Ed, what have you found?
So what I found is a new planet called TOI 6894b. And what's really exciting about this planet is, although the planet itself is just the size of Saturn, the star it orbits is only 20% the size of our sun.
I think I've worked out what these are for.
This football here shows the size of our sun in our own solar system.
With strange sunspots.
With some sunspots and solar activity going on. And then the red snooker ball is showing the size of the star, TOI 6894, relative to the sun. And then the small bouncy ball there is showing the size of the planet, both TOI 6894b and Saturn.
Saturn's the second largest planet in our solar system, and though it's a gas giant, it's less than 1/10 the size of the Sun's diameter. TOI 6894b, on the other hand, is almost half the size of its red dwarf host star. So is it unusual to have such a massive planet around such a small star?
It is unusual, yes, and the reason it's so unusual is because we wouldn't have expected that a star this small could have formed a planet this large.
Why not?
So when we think these planets form protoplanetary disks, these are huge disks of gas and rock and dust that surround the young star.
I've always thought of it as the leftover material from the star.
That's absolutely right. It's everything that's left from the cloud that collapses to form the star. And within these disks, the solid material, so the rock and the dust, collides together and over about a few million years or so builds up a very massive core that then will accrete gas and become the planet. But the problem around these very low mass stars is we think that these less massive stars have less massive disks. And so we wouldn't have thought that there would be enough material to form a planet this massive.
So what's happening? Is this some different form of planet formation, or is there something else going on?
So it could be a different form of planet formation, or it could be that we just don't understand the disks very well. So there's a lot of work going on currently to trying to understand these disks. And these disks have not been studied in large numbers, and these planets are very rare.
So this may just be the star that got lucky?
It could just be, yes, that this was a star that got lucky and for some reason had a disk that was a different composition than what we expected, either more massive or a higher percentage of it was this rocky material that could form the core of the planet.
Now, what about the planet itself?
So we don't know much yet because all we have currently is a mass and a radius and an estimate of what the temperature might be like.
So how will we find out more about it?
By observing its atmosphere using transmission spectroscopy and using telescopes such as JWST.
So what will we learn from these JWST observations?
So as well as learning what gases are in the atmosphere, one thing that we may be able to work out is the exact mass of the core. And using that mass of the core, that feeds back into what formation process may have caused this planet in the first place, whether it has a very massive core or a less massive core that could have formed through a different mechanism.
While powerful cameras in space hope to reveal the secrets of planets orbiting distant stars, it's by pointing a camera at the moon orbiting our Earth that you can capture a rather special image. Pete is on hand to explain.
While short nights and not particularly dark skies can make stargazing difficult during the summer months, the moon can always be relied on to delight, and this is a good time to look out for an effect known as the moon illusion.
This is where the moon appears huge against the horizon, and that is the key word, because it is an optical illusion that only occurs when the moon is seen near the horizon.
And the reason why it's currently a great time to look out for this illusion is that we're at a point in an 18.6-year cycle, which means the fuller phases of the moon appear low to the horizon at this time of year. You may have already seen July's full moon, which barely scraped 10 degrees above the southern horizon. That's less than the width of your clenched fist at arm's length. The shallow angle of rising and setting for the fuller phase of the moon means it appears closer to the horizon for longer than usual, and that's great for looking out for the moon illusion.
Good nights to look for it in mid-July will be on the 14th or 15th of July at around 2340 BST, when a waning gibbous moon will appear above the east-southeast horizon. Then again on the 8th and 9th of August, you can see the same effect with the full moon rising over the southeast horizon from around 2115 BST.
However, photographing these moons can be disappointing, and there have been many people who've seen a huge moon on the horizon, taken a photograph of it with their phone, looked at the result and been disappointed how small the moon looks. But for amateur photographers, it's all about the framing.
The key to getting a great picture simulating the effect is to ensure you have included something on the horizon to create the perspective your eye perceives. To do this, you ideally want to use a long focal length lens or a telescope, and you want to frame the image to include some interesting but distant foreground object in the field of view. Get it right and the effect can be very impressive.
Despite the long daytime periods, there's plenty more to see at this time of year. As always, you can check out my more detailed star guide, which is available at www.bbc.co.uk/Sky at Night.
Ever since I started out in research, I have just fallen deeper and deeper in love with exoplanets. Because we're not just discovering these incredible, strange new worlds, we're also gaining a deeper understanding of how the universe works. And I cannot wait to see what my guy Plato and, exoplaneters in general just go on to discover.
Surprising egg-shaped planets. There are eyeball planets. There are marshmallow planets, candy floss planets, and even
But before we go, there is one more thing. This month marks 25 years since Chris Lintop first appeared on the Sky at Night. And in celebration of that, here's some of his best bits.
And now, on to our main theme.
Here we go. Ready for takeoff?
And with me, Chris Lintop. Welcome to Sky at Night, Chris.
Thank you. Tonight's programme, we want to talk about the Saturnian moons, an annular eclipse, cosmic ghouls, galactic cannibalism. And I can't wait. It's going to be really exciting. We're watching the team at Mission Control and they look pretty calm. Calmer than I feel, anyway. And that was the annular eclipse.
Chris, where are you?
I'm at the Institute of Astronomy in the dome of my favourite telescope. This is the CAM in Cambridge, and we're just coming under the mathematical bridge. I'm here on the Isidis Planitia. I think you'd find Mars a pretty pleasant place to be. Well, it's flat and red. One of the problems in exploring the solar system are the sheer distances involved. Maybe we just need to think bigger. Seriously, this is too many Chris's. I don't think I expected that. Well, there it is, everyone cheering. It's been absolutely incredible. I think people are quite happy. So I'm not sure what any of that means. What do you reckon?
I don't understand it at all. Thanks very much, Chris.
And from the Sky at Night, good night. Good night. Good night.